Okay, so on today's lectures, we continue to prove the existence of solution to stochastic differential equation. And here I just recall the theorem that we stated on the previous lecture. So I recall that we consider a stochastic differential equation of the following form. So we have P from T, comma X from T plus sigma from T, X from T, here the Brownian motion, the I'm sorry, I forgot what letter I was used in the previous. Okay, and we have initial condition. I believe for Brownian motion we use letter B, and we know that at initial time we have some starting point x0. So we considering such Cauchy problem. And on the previous lecture, we discussed in what sense we understand that the process X is a strong solution to such stochastic differential equation. And we formulate the following theorem. We have some assumption on the coefficients of the differential equation. So we have uniformly Lipschitz continuity of B and sigma. And also we assume that coefficients do not grow faster than a linear function. So we have following upper bounds for these functions. And now we consider a non-random initial point. So under such assumption, we want to prove that there exists a strong solution to stochastic differential equation 1, and it is unique. I recall that on the previous lecture, we have proved that if we have a strong solution, then it is unique under this assumption. And now we are on the way to prove the existence of a strong solution to this stochastic differential equation. So let's start our proof. So as I said on the previous lecture, the proof based on the iteration scheme, and you saw it when you prove the existence of solution to ordinary differential equations. So this maybe you will be familiar with this. So what is the steps of proof? So step first. So we put the first iteration to our solution x t. We will write here. Let me x first at t. This is just initial value that we have x0. I'm sorry, let it be the zeros approximation. Then the first approximation, we will define as following. So we consider integral form of our stochastic differential equation, but instead of values here, we write xt, but now I will write here the previous approximation to stochastic differential to solution. So I write in such form: t sigma x0. as dw/db. So here, as you can see, this is not the equation, because we have here some random, or in this case non-random functions. So this is just a definition for this process. So what should we check for this process? First, in our definition, we say that the process is a continuous function. So what is about continuity of this process? So as you know, since we have a continuous function b here, then the first integral with respect to ds, this is the integral of some function, and you know that the integral is a continuous function. This is from your calculus. So now what is about the second part? So the integral with respect to Browinan motion. Let us check this in the general case. In general case, let us consider some integral of some function h, as we denoted, with respect to Browinan motion. And I will denote this process as I from t. So this is the eta integral, and I am wondering if this process is a continuous process with respect to t. So what do I know? If h is a step function, so assume you remember that we approximate the eta integral of such form with these integrals of step functions. So I assume that h of s now is a step function. For example, it is x equal to psi k, indicator of tk plus 1 from k, for example, from 0 to some m. Now, how does this integral looks like? So for t from, for example, from tk to tk plus 1, my integral has the form. So now this is a step function, so I can write sum, where h, sorry, here k, I will write j. Here increment of Browinan motion t j plus 1 minus b from t j, j from 0 to k minus 1. And here I have additional term psi k, and here increment of bt minus b from t k. So on the picture, we just define the eta integral here. If I have tk plus 1, I consider integral just up to time t. So I consider this increments of the intervals here. And the last part here, we have not the whole subinterval in my integral sum, but I have the interval from tk to t. So from this, you can see that such a function is a continuous with respect to t, because Browinan motion, as we said, has a continuous trajectory. So for such function, e from t is a continuous process. Now we want to approximate the integral with respect integrals of step functions hn. So to see that their obtained limit will be finite or will be continuous, we need some additional knowledge of how we can estimate supremum of difference of the integrals. So let's write what I mean. So assume now so this was the first step, this is the second. Let hn is step functions, step processes for which the eta integral is well defined, and we assume that hn approximate h in norm that we defined as, I just recall that this is norm of the following form, h from s ts. So you can recall this here. I'm sorry, I should take some the interval that we are considering now. So we prove that the eta integral is continuous on the interval from 0 to t large. So now to prove the continuity of limit integral, I will need the following estimation. So if I estimate the maximum on the interval from 0 to t of the integrals h from s minus hn from s the Brownian motion of s to the some power, then I will get that I have uniform convergence, yes, if we have here maximum, and I will obtain some upper bound that converges to 0 as n converges to infinity, then everything will be fine. But now I need to estimate such moment of maximum of the integrals. And for this, I will use following inequality for martingales. Recall that we proved that integral is a martingale. So for martingales, we have a lot of useful inequalities, but since we have no much time, I will give to you it without proof, but you can find it in the textbook about some martingales. So this is known fact. So let me just formulate the general inequality for moments of maximum of martingales. So this is so-called Burkholdt-Davis-Gandhi inequality. This is called inequality for martingale. And let me formulate it in general case. So assume we have martingale MT, so T is greater than 0, is martingale. And we need the following also notation. And I will denote the process AT, T greater than 0, is a non-decreasing process adapted with filtration. Adapted with filtration. FT that generated by martingale M, I will write here letter M for this notation, such that MT square minus AT is a martingale again. So you can find in the literature that such process AT is called a quadratic variation of martingale. Quadratic variation of M. So, for example, for Brownian motion, you can recall that MT is a Brownian motion, then the process AT is just T, yes, because we proved that Brownian motion to the square minus T is a martingale again. So it turns out that for each martingale which have second moment, there exists such a process AT, and it is used in the following inequality. So the Burkholder-Davis-Gandhi inequality are formulated in the following way. So there exists a constant C small, which is dependent on P, and C large, which is also dependent on P. And the P is greater than 1, such that we have the following estimation that expectation of maximum of martingale on some time interval MT to the power 2p less or equal than C large. And here I write expectation of this process A at time T capital to the power P. And I have, so this part we will use now, but also there exists a second estimate, so we can write the estimation from below. It's greater or equal than C small, here the same T. So here you can see that we to estimate the moment of maximum on the interval, we need to know the moment at the last time T capital of this process A. So what is about the eta integral? Now let us come back to eta integral. Back to process I of T that I saw from 0 to T, H from S, D, B, S. So now this is my martingale, and I state that I have now I need to find this process AT. So let us check. That if I take I to the square of t and I will subscribe the process, the integral from 0 to t, and here this such process. Then this process with respect to t will be martingale again. So martingale, so let's check it. It's not very hard. So what we need to check, proof for this statement. So we, if I consider this, let me use here another letter R, for example, because now I will take the conditional expectation with respect to S. Remember, and I will take it, take the sigma field that generated by Brownian motion. Yes, recall that we proved that eta integral is a martingale with respect to filtration that's generated by Brownian motion. So what should I do here? Here, since integral on the interval from 0 to t is equal to sum of two integrals of here, let me write notations. This is integral from 0 to s. In my notation, this is I from s, plus integral from s to t r db. So I use this property and put it into the square, and what I will get that I have here I square from s plus 2 integral from s to t h from r d b from r multiplied by e of s plus such integral h from r d b from r to the square, and the same I will do with this integral. I will split it into two parts, r minus s to t h squared r t. Okay, so what we can see from this to writing, this part is measurable with respect to sigma field Fs generated by Brownian motion up to time s. So I write it without conditional expectation, I square from s. This part is also measurable with respect to this filtration, because we know that we assume that our considered process is adapted to sigma field generated by filtration B, by process B. So this is also measurable, and I write it without conditional expectation. Okay, so this first that we need, and now we will see that the remain terms are equal to 0. So what do I have here? I have here also, let me denote, this part is measurable with respect to sigma field, so I write it before the conditional expectation and to here. And here I have conditional expectation, I'm sorry, from S to H from R, D, B from R, with respect to F, S, B. And what do we have here? This part, then this part also plus conditional expectation from S to T. to the square, and I need to write condition with respect to s. Yeah, conditional expectation, and this part as well, minus conditional expectation of ST h square of r dr with respect to fs. So what do I know about the expectation of integral? So here again, if you consider the step function, you will see that you have here the sum of some part here, which is so you will have the increments of Brownian motion that are independent of this sigma field. So you will have 0. Okay, and it is also almost the same here. We considered, you can remember that we proved that the expectation of the square of integral is equal to such integral, to expectation of this of such kind. So here just a difference that we have the conditional expectation, but it is too easy to prove that this conditional expectation is equal to such conditional expectation. This is the same proof as we done it for expectation without conditions. So because we have here increments that are independent of this sigma field. And this integral is equal to 0. So this two part cancelled, and we have what we need. So we have just this part. So this is equal to 2 square s h square r. So here we finish the proof of the statement that we have that this process is the same as this process A in definition for general martingale. So now I want to apply this Burkholder-Davis-Gandhi inequality to eta integral. So let's rewrite that Burkholder-Davis-Gandhi inequality for eta integral have the following form. I will write just the first one. So if I need a maximum on the interval from 0 to t of some eta integral to the square, I'm sorry here, 2p, this is less or equal than some constant and the expectation of the integral from 0 to t h square of s ds to the power p. Okay, so now I will use this inequality. Recall, let us come back. So that this is easy now. If I have a step function, come back to continuity. So I estimate maximum on the interval of difference of two integrals bs to the second power. I just here p is equal to 1, and this is less or equal than I'm sorry, p equal to 2, because here no, So here, expectation integral from 0 to t h square of, oh, I'm sorry, from s minus h of s. I'm sorry, we have here inequality only for p at 1. Let me write here square. So here I write 4 and here the second moment. So, and we know that this converges to, write ds. We assume that this converges to 0 as n converges to, and so we have uniform convergence. So to go from n to t, n to s, d, b from s converges uniformly. To the integral from t h from s, d, b from s. And we can choose such a sequence of approximations that we will have here convergence almost sure. So the integral is a continuous function. S is continuous. Okay, so this was such a technical proof, but now we know that our process that we define for approximation, first step approximation. So x from this follows that the first step approximation is a continuous function. Also, we can estimate now the moments of this process. So we will need in following, in our induction, that also we can estimate supremum on the interval 0 t of this x1 from t to the square. So this is the same. You just write the formula for this x1, and we will see that it is equal. We have 3 summands, so I write, I'm sorry, to the square plus integral from 0 to t supremum also 0 t b from s x0 from s d s to the square plus supremum 0 to t, and here integral sigma from s x0 from s d b from s to the square. Okay, and now I can again apply Davis-Gandy inequality. I'm sorry, got here expectation, and this is it can be estimated by here x0 to the square plus here I will use again Cauchy inequality to put the square into the integral. So I will have here a constant t, and the expectation of here from 0 to t b from s x to t large, to t x0 from s ds plus sigma square from s 0 from s. So this summand, I recall that this summand from the Davis-Gandhi inequality. And I continue here. I'm sorry, let me write ds here, ds. Okay, so now I will use my assumption for coefficients b and sigma. I recall that by assumption, what do we have? We assume that for b and for sigma, we have the following inequalities. It's less or equal than some constant plus model x. And for sigma, the same. So I can write here, I can continue this inequality using this assumption. And here I will have some additional constant t multiplied by constant c, this. And here I will have the integral of these upper bounds, but the integrals do not depend on t, so I will have just here t squared and expectation of 1 plus modulus x over. Oh, it depends. I'm sorry. From, let me write from 0 to t, x0 formally depends on t, yes, to the square, because we have here squares. Okay, and here, I'm sorry, here also I have square. I missed this one. Okay, so we have such upper bound, and I can estimate this value by supremum. So let me write 0 to the square plus now t squared c, and here I will write 1 plus supremum from 0 to t x 0 from s to the square. Okay, so now that we will use on the later steps the same procedure to estimate the moment of the next step approximation by moment. Oh, I'm sorry, I forgot here moment. By moment of the first step approximation. So this is the main idea. So if we have that our initial condition now it is not random, so we have that supremum on the interval 0 t of our first step approximation is to the square less than infinity. So now let us do the next step. Next step, we assume that we have k approximation. We have x1, x2, and xk are defined. And we assume that we know that supremum on the interval from 0 to t, x k from t to the square less than plus infinity for all k's. Right here, yod. And I define the next approximation x1 from t, which is, as you can now say it to me by yourself. So this is familiar to you. We just substitute to the integral form of our stochastic differential equation the previous approximation here, k from S ds plus integral from 0 to t b from, sigma s xk from S, and this is integral with respect to Browinan motion. Okay, so we define such process, and the same proof as we have done before for proving the continuity or for proving the bound for supremum of the squared of this process, we can find that we can prove first that you can see that this is also will be a continuous xk plus 1 is a continuous, and the expectation of supremum of 0t is bounded. So the step of the proof the same as we already done. So we have what do we have? We have a sequence of continuous processes. Also, you can see that they adapted with respect to filtration of Browinan motion. Let me write k plus 1 is adapted to filtration that generated by Browinan motion. I will write in this notation. So this integral is well defined. And now what do we need? We want to prove that this approximation converges to some limit, and this limit will have the same properties. So the question is, when I will tend to k to infinity here, what limit do I will have? So we can assume that if the process convergence, then the limit will be the solution to stochastic differential equation. Yes, if I prove that this limit exists, I will have integral form of my differential equation here, because the function b and sigma are continuous by our assumption. So we will have the solution. But we need to be sure that this limit is a continuous function as well. So we need uniform convergence of this sequence xk. Yes, we know that the sequence is a continuous, and we will consider the uniform convergence on some interval. Then the limit will a continuous function again. So to do this, let us prove. Let us prove that limit exists, t exists, it exists, and equal to some process xt, and xt is a strong solution to our stochastic differential equation. So how we will do this? So let us denote by row with index m from t the expectation of supremum from 0 to S, so from T, X T, so from X from S, here M plus 1 minus X M from S to the square. Okay, let's consider such functions. So I will obtain some inequalities for them. So let us consider M plus first one. Let me write here M plus first. So this M plus 1 and so on. Okay, so I want to estimate this part. So here again I use inequality, Burkholder-Davis-Gandhi inequality as well. So, and the same procedure as we have done before here when we proved this part, but we will consider just difference of two functions. So this is the, let me write here the first step from 0 to t. Here I will have integrals from 0 to t as x m plus 1 from s minus b from s x m from s. This is just the definition of functions m ds plus 0 to t sigma from s m plus 1 from s sigma from s x m from s dw from s, and this is 2 square. And now I will use their uniform Lipschitz for B. Recall that B and sigma are uniformly Lipschitz functions. So for this difference, I will use Lipschitz property, and as well I will use Cauchy inequality to put this square into the integrals, and for this part I will use Burkholder-Davis-Gandhi inequality. So here it's not hard to see. Let me write the answer. So this here I will have some constant first. This is constant from Lipschitz continuity and from Cauchy inequality. So that's constants depend on t as well. So this is less or equal than expectation from 0 to t. And here I will write x m plus 1 from s minus x m from s to the square ds. And the one step I want to have here is supremum as well. And this is not less than some constant, and here integral from 0 to t. I will write just here a supremum from the 0 to point s. Let me write this supremum from 0 to s, and this m plus 1 from r minus x m from r to the square ds. So now you can recognize here that what we have. so we have, I will write in one line, so you will see we have some constant. It depends on t large, so as we consider on the interval from 0 to t, I will write here t large, and here interval from 0 to t, and here you can recognize here, what is this? By my notation, this is rho. Oh, I'm sorry, I do this in the wrong way, because when I substitute, I need to have -1 here. Yes, -1. I'm sorry, please correct here, because when I substitute, I do -1, and then everything will be fine. Okay, m -1. So this is in my notation, rho m from S, because it depends on S. So I have the inequality that this is less than rho m from S ds. Now I can continue this inequality. Yes, because we have inequality for all m, I can write here C integral from t rho m from S ds, and this is less or equal. Again, here I will have c squared now, and here I will have integrals from 0 to t, 0 from S, rho m from R dr, for example, and so on, -1, of course, we put here -1, and so on. Let me use much more appropriate notation. I will have c to the power m, and here integral from 0 to t, integral from 0 to t 1, and so on, from 0 to t m -1. And here I will have rho first from S dt m -1, dt m -2, and so on, dt 1. And ds. Okay, and also we can prove that this first is also bounded function, because we have just supremum of the integrals when we have initial point in the coefficient. So this is bounded by some constant, for example, k. So this is less or equal c to some power to power m, here some constant k, and here's the integral, and you can say me to which this integral, the answer for this integral is dt m -1. So what is this? You can take this integral step by step, and you will see that this is equal to t to the power m. This is t, and it divided by m factorial. So this is just an exercise from calculus. So what do we done for now? So we have we can have from this that if I consider such a series, that probability of supremum on the interval from 0 to t capital, the difference t minus xn from t. So this is our rho is greater than 1 to the over m plus 1 to the square. I write here 1 because we start from 0. And this supremum I can estimate by Chebyshev inequality by the m plus 1 to the fourth power. And here I write just expectation of supremum to the square x t minus x m to t to the square, and we already estimated this by this one. Yes, so I'm sorry. I use this upper bound, and I have convergent series. As you see, here some constant c t to the power m divided by m squared, and this is less than infinity. So as you recognize, when we write such sum of a series of probability, we want to use Borel-Cantelli lemma. So by Borel-Cantelli lemma, we have what? We have convergence. Yes, we have that this series supremum t capital xt, I'm sorry, x m plus 1 from t minus x m from t from 0 to infinity converges so this is less than infinity, yes, almost surely. So we have from this follows that the series, if I consider the series x0 plus the series of the following type minus x from x and from t, such series converges uniformly on the interval from 0 to t, almost surely. So we have some limit process. Yes, let me write, for example, if I have here not the infinity, but for n capital, yes, what do we have here? From other side, this is equal to x0 plus just this x0 will be cancelled, so we have here just x and from t. So if the series converges uniformly, then this sequence xn is also converges uniformly. So we see that this sequence has continuous limit. So let us denote x from t is limit, and we prove that this limit holds almost surely, and this limit is uniform limit. So this process is continuous. So this is almost the end of the proof. So what do we need to say? That now we can get to the limit in our integrals. So come back to, we remember that this process has the form from 0 to t, b from s, x, k from s, ts plus sigma from s, k from s, tb from s. Now get the limit with k converges to infinity, k to infinity. We will have that the process x satisfies this integral equation. So we have that this is also fulfilled. So this is almost done. We prove that the process is continuous, and you can remember that from the definition of strong solution, you need to be sure that this integral is well defined. So you need to be sure that the second moment of x is bounded as well. So this can be done because we have the upper bound of supremum of second power of processes x, and they are bounded. We have proved this. So we have here bounded. We have here dominated convergence. So we can get by dominated convergence theorem, you can get the limit of that's right x from t to the square supremum over 0 t capital is less than infinity. This can be proved. Because we have the same condition for the sequence xk. So this is it for the proof of the existence. And since I have no time to consider the Markov property of solution, I will give here some remarks. First, you can see from the proof that we can consider not only deterministic initial point, but the random initial point. So let me write here that we can take a random initial point at t equal to 0. So this means that I have initial condition psi from 0, x from 0 is equal to psi, but I need that psi is independent of Brownian motion. Of Brownian motion. So the proof will be the same, but you need to be careful when you consider expectation of all integrals that we considered. So you need to take first condition. So when you consider some expectation of our integrals, you need to take first the conditional expectation with respect to psi, and then we can take it as non-random point. So this is the idea. And the second, that we can consider the solution as a function from initial point. So what do I mean? Let us consider stochastic differential equation as before. X t is equal to b from t, x from t dt plus sigma from t, x from t, d b from t. But now I want to consider the solution that starts from some point, and I will consider how it depends on this initial point. You can remember from your course of ordinary differential equation that the solution of differential equation depends on initial point continuously. So the same we have here as well. So let me denote by x, and here I will write this initial point psi from t solution to this. I will write to this stochastic differential equation, and it is it can be shown also that then expectation of again supremum on some bound interval, if I consider two initial points psi and eta, for example, to the square, this is can be bounded by some constant, and here's the expectation of from psi minus eta to the square. So here you can see that we also have some kind of continuity, and this is not hard to see. Let me write some two lines for proof. So if I have supremum of these two solutions, eta from t to the square, this is less or equal. What do we have? We have here, I will have three summands, supremum 0 t. I will have three summands psi minus eta plus integrals from b from s x psi from s minus b from s psi eta from s ds plus stochastic integral s psi from s minus sigma from s x eta from s, okay, dp from s, and now to the square. So I will use here the inequality to call a plus b plus c to the square less or equal 3a squared plus b squared plus c squared. Okay, so this is less or equal than expectation psi plus minus eta to the square, and this we already know how to estimate. I will use Lipschitz continuity for b, and I use the same inequalities that we used already for the stochastic integral. So I will have the integral from 0 to t. Here expectation, and also I will write supremum to get the same as in the right part. I write here to t capital. I can do this because I will have squares from 0 to t, x from psi s minus x from eta s to the square ds. So this can be done. And now what do we, you can see here that also I forgot here some constant. I will write here C1 and here C2. So we have on the left hand side the function, and you can see the same function in the integral. So you can recognize here the inequality, the Granol lemma. You will have the same the upper bound that we discussed. Yes, we have this supremum 0 to t x from psi t minus x from eta t to the square. This bounded by this some constant, and you can recall that you have some exponent to the power t here. So I will put together this into one constant, big constant c. But the main part that we have here, the expectation of distance between psi and eta to the square. So from this, you can see that if psi converges to eta, or it's small in L2 sense, then the solutions will be close to one to another. So this is the from this follows that x from the first coordinate I will write here, for example. I will write here dot. So if I consider such a function with respect to this variable, this is a continuous process. So this is to remark about the stochastic differential equation, and then on the next lecture we will use this remark to consider the Markov property of solution to stochastic differential equation. This is similar to Markov property of Brownian motion, and as you can remember, the distribution of trajectories. So this is just an answer for the next lecture. If I consider some past up to time t of solution, yes, this will be x from t, and I consider conditioning up to all history, then the trajectory will depend only on the value at the last observable point here. So if I observe up to time t, so the next value will depend only on this position and not on all trajectory. So this is Markov property, and this also true for solution to stochastic differential equation. So let's postpone it to the next lecture. And maybe you have a question about this part of lecture about the proof of existence or maybe you have questions about the previous lectures, you can ask me. Then, if no questions, I will stop the